Yeah, well, I will see how many. Oh my god. Oh, there's well.
Yes, every Tuesday. No, that's okay. That's why we bought them.
Right. Oh yeah, well, you might wanna.
Don't worry, I'm out there.
By the way, if you plug that in your computer right now, it's gonna start showing you rainbow of colors, which is it's normal. Just say.
Oh, it doesn't. It's just calculation.
Wait, so every. They all have okay. Oh, that's fine.
It's like 2 weeks. Oh, it's beautiful. Yeah, I don't know. But like, I mean, this one's nice.
All right. Oh, whoops.
Sorry, everybody. We'll give you a couple minutes to sign in, and then we'll get started shortly.
Satanic. You know, Satan was an angel too, so it's not really.
So, y'all want to.
Yeah, it's better in the computer. Yeah, I think a lot of y'all just are already in a class that uses this, right? Yeah. So again, this presentation is really for, at least for today, as for folks who have not gotten the basic info yet. So I'm just gonna repeating stuff that you will see with Dr. D's class. How many of you are in Dr. D's course? Just wondering. Just one. Oh, okay. Ooh, Dr. Lay is the harder version. Nice. She's gonna do assembly first, right? This year too. Nah, you're in the nicer class.
Wait, what's the other?
Dr. Lay, oh, he will teach you assembly, C, all of that. Just make projects harder than they should be. So, good luck. I took Dr. D's, so.
Okay, you ready to start whenever you are.
Cool. Good morning, everybody. I'm Navia, and this is an introduction to a TIVA-C. Cool. All right. So TIVA-C, also called Launchpad. I think Dr. D will call it Launchpad. I don't know what Dr. Lay calls it. It's a family of microcontrollers from Texas Instruments, which is the leading supplier of MCs in the world. And also it is relatively inexpensive, which is one of the reasons why we have this in this college. Because if you're not in the business college, you don't really get expensive stuff in here. The TIVA-C has a 32-bit CPU, which can run up to 120 megahertz per second, just from 80 to 120. I don't know about Dr. Lay, but if you're in Dr. D's course, towards the end of the semester, you will be working in projects where you will be increasing the frequency of the clock. And you'll use inbuilt timers to just really control the things that happen there. And for this particular TIVA-C that we have 40 GPIO pins. There are other chips in this family that have up to 80. And again, each one of these pins can be analog or digital, depending on how you configure them. And the last two bullet points are one of the really the main reason, other than money, is why it's being used. It's because it's a ARM Cortex, which is the industry standard for pretty much every embedded systems you'll see. And the reason ARM is preferred, I think Dr. D will get into that in her book. But the reason why it's preferred is basically it makes better use of assembly into machine and then the actual microcontroller as opposed to the previous versions. Okay, and in this slide, we will just sort of compare I mean, just general information on, you know, why TIVA-C versus Arduino and like BeagleBone. I personally never worked with BeagleBone before, so you know, some of you will know before better than me. There's also information here that some of you may or may not know, especially when we go down to execution time. That's something you will definitely learn in computer architecture. It is generally what it's called is how fast can your processor, you know, perform these instructions, and that depends generally not just on your clock speed, but also how big your bus is and everything. And just because you have a fast CPU, right, it doesn't mean that it's actually the best. Okay. And the memory we have on the TIVA-C is a flash memory. So it's one of those non-volatile memory that is both readable and writable. Towards the course of your semesters and whichever courses you take, you will get into why some memories are preferred over others. The one that is in the TIVA-C is actually made of MOSFETs. It's the more expensive end, and the reason why is because MOSFETs are more stable as opposed to the capacitive ones, which are in your hard drives and the other ones. And capacitors, they need to be refreshed every now and then, so they take more power too. So that's why they dissipate heat a lot, right? Most laptops, at least my laptop, has MOSFET memory, I think. Anyway, that's why it's also more expensive, because MOSFETs. And the reason why MOSFETs are more stable is when you get into digital electronics, if you are in EE, you will have to take that. You'll find out that their I/O characteristics versus voltage and currents, it's more stable, so there's more cutoff regions, right? And we operate within those bounds so that white noise is canceled. I didn't put that graph here. Maybe next time I'll show y'all. Okay, let's go here. And again, from now on to pretty much until we get to the code composer setting up slide, all of this comes from the data sheet. I should have it on the drive. If I don't, I will give it to you in our next meeting. So right here is our top level diagram of the TIVA-C, of the chip that's in the TIVA-C. So there's two chips that you notice on the TIVA-C, right? There's two black ones. The one in the middle is the one that we actually get to use. The other one's for like the TIVA-C itself. And the actual chip is called TM4C123GH6PM. That is the actual microcontroller. And if you look at the top half, that's the actual CPU. The CPU is in the ARM Cortex M4F. That's the CPU, and everything else is your module that you will make use of in this workshop as well as in your classes. And also, the farther down the list you go, the slower it's supposed to be. Of course, you won't be able to tell humanly, but if you go down to execution time, it's slower. And also, the closer you get to the CPU, the more expensive things get and the faster they are. So you look at SRAM and flash memory, right? They're really so expensive when you start making them in bulk. It's because they're closer in memory hierarchy. Again, all of this should be covered in your computer architecture class when you take it. And again, none of this is supposed to supplement anything, right? Okay, so in here, this is what your CPU looks like in the processor itself. And this is actually pretty important if you're gonna be an engineer, at least for your course field. Not this itself, but like the general structure, right? And I think if you spend some time, you know, before you get to those courses, like especially computer architecture, trying to understand how this works, it will help you, because 90% of the class is genuinely for you to be solving problems relating to this. It won't look exactly like this. This is a little bit too complex, even for me. But the way it generally will be structured in those courses, in that class, is like you'll have data coming in. You'll have your mux right here, like this, right? You'll have your registers. You'll have your ALU, other arithmetic thing, components that are inside the CPU, like these. And then the questions would be like, hey, what does this instruction do? So this is what it will look like. I can't give that example with this because again, this is a little bit way too complex. I'll try to do one next time for sure. And in here, this is probably the thing that you will obsess a lot in Dr. D's class. From R0 to R12, this is what you would be using to basically do all of your coding. These are registers. They're all 32-bit. Least significant bit first. No, most significant bit first, sorry. R0 to R12. There's no particular reason why they're called low to high. There's really just numbers. I think the more important ones are from stack, pointer, link, and program, and anything below that you will generally not care unless you have to care about it, which I don't. I've never used that, so I have no idea how to use it. For stack pointers, they're important because that's where they hold the address to your last pushed saved value. Okay. If you're not familiar with stack, they're like you can, or they're one of the data structures that you will have in in the computer field. If you take data structures, if you're a computer engineer, you will be taking data structures. You'll be using that there, and over there you'll find that stacks are not exactly the most helpful, but they are helpful. And the reason it's called stack is because you're stacking memory on top of each other, and so you have to push and pop to use it. Each one of them is going to be byte addressable, which means that you can go to specific memory by writing code to it. In assembly, you'll have to write like a hexadecimal, I think 8 digits of it. When you write in C, you just tell it to go there. Linked register is actually probably the most important one. And the reason why is because it holds your address to the branching, right? So let's talk about, whenever you're coding in a structured language, it's easier to understand in a structured language as opposed to dynamic ones like JavaScript and Python. Because for structured language, you go from top to bottom instruction, whereas for Python and JavaScript, they're dynamic, so they just start where they want to. So whenever you write a function, you define it a function, and when you call that said function, right, the execution just stops there, and it looks at the name, which is your code, to where to go in memory, because all of your code is stored in memory. And whenever it performs its intended function, it has to return. And the way it knows where to return is it's by using the linked register, right? And so that's why it's very important. Whenever you are coding in assembly, you need to keep track. Whenever you use your jump instructions, which is your be equal, BEQ, branch equals, or whatnot equal. There are a couple of them. You have to keep track of the memory, the address in linked registers, and that's where the stack comes in. Because if you are using nested, you'll have to push and pop as every time you go. And again, Dr. D will give you a lot of this complex examples, and yeah, it gets harder. Program counter, it just stores the address of the next execution, next memory. Next set of instruction in memory. You can use that too as well, as opposed to use as a branch. So you just gotta play with it, but they're all very important. If you don't have that, then your program really will not be able to run properly. Okay, in here, nothing too important actually. You'll just see this again. I just wanted to show you all that they are indeed read and write. And again, this is on the data sheet. Okay, and this is what your registers look like, generally speaking. I don't think you'll ever actually use all of 32 bits. You might, but most often you'll be using a few bits in here, and sometimes it's important. But other than that, there's nothing much here. If you look in the data sheet, I know I didn't show it here, but there are few like places in these registers that you have to either turn on or turn off. That will determine if they're analog or digital, or like if they're input or output. And you can also to configure them as analog or digital. And on the TIVA-C itself, there are some ports that you're not really allowed to use. And some ports, actually, you won't even get to use all 12 of those registers, right? I think port F is one of the ones that are used most commonly, where you get to use all 12 of those. Some of the ports have restricted access. That's just the way TIVA-C is. All of that is really clarified in the datasheet. Datasheet is your friend, really. I think all of you guys are upperclassmen, but if you are not, you should learn how to use datasheets, because they'll help you in pretty much every class that you take, advanced circuits. And the stack pointer bit fill, again, same thing. They're all 32. I just all of these you can really just skim over. I just added them here just to show y'all what they look like, because my assumption was y'all never seen it. I think most of you have seen it. There you go. Again, as I said, you'll see this a lot in Dr. D's microprocessors, of course, especially because I think Dr. Lay just likes to work with C in his courses. So you probably may not need to care as much. And from here on, I will be showing you some module diagrams of the modules that I think I'll be focusing on in this workshop. It's ADC, analog to digital converter, your UART, and your PWM modules. So you have you have about 12 of these. Yeah, 12. You have 12 analog channels for ADCs, and I think you have two identical modules. They can all operate individually and independently of each other. This means that they can execute programs simultaneously, right? And the reason this is important is because in the real world, quote unquote, you don't code with while loops, right? You code with RTOS, which is a real-time operating system. So like your laptop right now is coded with RTOS. If you go to Task Manager, you'll see BIOS and everything else, and that's because it's coded with RTOS. You'll see that in your embedded processors class. And what executing independently is important is because you can type and use your mouse at the same time. And the reason why that happens is because you have modules that operate independently of each other, right? With different threads and whatnot. So we will try to do that here, possibly. Okay, and the next one, again, none of this is really important. Again, this is just to show you what it looks like inside. Like on the left-hand side, you have these inputs, and then you have just muxes, right? It goes inside the controller status. All of that. It's not actually of use to us here, but it's just a datasheet information. Maybe it would be helpful to you. Okay, for UARTs. UART is also one of the things you will be using in Dr. Lay's future classes. It is very common, actually. I mean, it's also the easiest to use in terms of serial connection, right? Serial means a sequential bit exchange, but also it's one of the most more restrictive in terms of information passing, actually. Because I think you can only have about 8 bits, and in there, if you have safety checks, then it's actually even less to use. So it gets very pensive to use, actually. We have 8 UART modules. It has a programmable baud rate generator. Baud rate just means it's a rate at which information is transmitted, and it's in beats per second. Let's get Ethernet 2. You have bits per second, right? It's sort of similar in the same family. The TIVA-C we have here for regular speed allows up to 5 megabits per second, and to do that, you divide by 16. Again, the formulas I have not shared here, but there's a formula to get your baud generation. It's going to be, you'll use values from your data sheet, but usually we will have a formula to generate the baud speed, and that's important because then that determines the frequency at which you operate. Also, it also makes it unique so that the other devices can then connect to your device. And the key thing to note here is the faster you want to go, the smaller the number you divide by, right? And my example that I thought of was using like an example of Coulomb's law and the gravitational law, right? If you want the greater force, you divide by a smaller number. But yeah, that was just something I thought of in the morning. Anyway, we have FIFO trigger levels, and all of them, again, there are portions. All of this I will get there when I actually do the UART specific workshop eventually. We have UART signals. There are other microprocessors from TI, like the MS430. It doesn't have a lot of UART because it's not exactly the optimal one to use. Sometimes you'll use I2 squared, which is synchronous, which means that it relies on the clock. This one doesn't. So this one you can actually use with RTOS pretty easily because it doesn't need the clock for you to use that, right? Asynchronous connections like I2 squared, I2C, requires the clocks. It's less friendly to use, but you can actually transfer more data, and also sort of relatively more safer because the clock will check in, determine when the data is coming in and when it stops. Whereas for UART, you don't. So you have to actually have parity bits. And over here, these are just the pin numbers on your TIVA-C where you use the UART connection. This one's relatively simple to use. And for real world applications. So there's some examples of some of these modules. Your phones use ADCs whenever you're calling somebody. Your analog voices get transferred into digital signals, which then also get translate back to analog for you to hear. Digital oscilloscopes use ADCs for converting analog signals into digital signals, right? And UART is used in GPS receivers and Bluetooth modules. Also, I will be sharing the slide. So all of these things on the notes section, there's the web pages where I've gotten this information for. So if you want to further read, you can do that.
I've shared it on board. I've just shared it in the chat.
Cool.
A link to the PowerPoint also for the ID.
Yes. So all of these slides have like for the more important one, there's a notes section, and all of them I have linked to like the specific websites and stuff I used. So do you all have your Code Composer Studio set up? And all online folks, I don't know how many are online. Do you have it or not?
Yeah.
Okay. Because if you have it, then pretty much that's sort of the end. But if you don't have it, I can walk you. I will still just walk you through it, just in case nobody has it. All right, so you're supposed to go. Oh, oops. If you follow this link, you'll get to. I didn't really show it. Can you see? Oh, you can see this. Okay. So you'll get to here. And you can download this Code Composer Studio. Also, not every class will use the same version, because the thing with TI and the issue with almost all open source softwares is that it's not really taken care of well. So they will update things and you don't know when or how. Like, for example, just like a year ago for Dr. Lay's class, we used version 6, right? And I think version 9 was out. But now he's using version 10 because of reasons. So you can get your download versions here. When you go to download options, view all versions. Well, I right now I have this 10.4 on my computer here. My computer at home, my PC at home, I have the 12 version. So it's really up to y'all. Not really. No, not quite. No, so I use 12 and it works at home. So like, because you have to also download the TIVA-C software, and they also have the latest version there too. Yeah, so Dr. Lay just prefers older version because I think he just has examples. Yeah, but so I think for classes you'll probably be using older versions, right? So I would recommend using just like Leota, like maybe 10.4 is the one Dr. Lay is using currently. Probably go with that. I think Dr. D is using Keel for our classes, right? Yeah, she always does that. So you're good. The thing with Keel, it's slightly easier when you use assembly as opposed to Code Composer Studio. But when you're trying to use RTOS systems, Code Composer Studio is easy. Like I had a friend who took Dr. Lay for like a second class. He used RTOS with Keel and it was way harder. Keel is better for assembly because when there's a debug process and you can actually see all the machine language right there on your screen as you go through instruction by instruction. Dr. D will show you that. It actually is pretty helpful. Okay. So after you download your selected versions, let me go back to the presentation. One of the things I hate about Zoom is blocks the it blocks the slides. At least the tab. So wait, I need to get back to the tab. Oh my. Okay, wait. Okay, there you go. So I'm trying to go back to the slide. After you download, also, I don't know how you guys are doing it for your classes, but just for the TIVA-C itself, you can just get this one. It'll save you space, right? Because I recommend doing a custom one unless you want to get everything, but you really won't be using everything there. Because with everything, you're wasting about 4 gigabytes of space, so gigabytes of space. If for just TIVA-C itself, you want to get that TM4C. So when you do custom installation, it asks you what do you want to download. You just get this TM4C12X ARM Cortex, right? And after that, and then you just do your setup there. After you finish setting up, you want to go to this website, which I do not hyperlink, but you don't even have to do it. You can just Google TIVA.
I've posted it already.
Oh, cool. Nice. So you come to your development kit, right? This is where it has all the libraries, by the way. So you need that. If you don't have this, it's your code is not gonna work. Right now the most up-to-date version is 4.2. The one that I am using in my computer is 2.14. I believe that's what Dr. Lay's class is using too. And in here, you also have this option to download the entire library for all of it, or just download the one specific to our chip on the board, which is this one, right? Because again, TIVA-C comes with a lot of them. So I personally have this here. It's just because the least amount of space. And after you install that, well, let's go back to the presentation. Oh wait, sorry, this chat's. Oh, okay, never mind. if there are questions. Okay, so I'm assuming everybody has this. After you install all of that, we will get to. I was like, is there an earthquake happening? Okay. After you install all of this, this is where the little bit of extra setting up you have to do. So the images here is from actually like the latest version, right? It's not the one. If you have older versions, like the one in my computer, you won't see this. It's similar. What you want to do is you want to click on new project, and after that, the screen will generate. It will also actually ask you to verify your workspace. It usually uses your library. You can choose wherever you want it to go in your computer. After you verify that, you'll have this screen right here. And in the top and for target, you'll have options like TIVA-C series or TIVA-E or something like that. Actually, I can probably show it to y'all right here, can I not? I think I can do it here. Hold on. I'll just run it with a real life example. Oh, not this. It opens, never mind, sorry. Code. There we go. Yeah, I have 10.4. Okay, let me show it here. Okay, like I said, the moment you open it, it asks you to verify your workspace, how to browse. You'll open an older project that I do have. Also, I think in the real workspace, I think your companies will have their own preferred versions of embedded software. So like Code Composer Studio is actually based on Eclipse. So you can actually just use Eclipse IDE for embedded. I mean, not anymore. They can see this. Yeah, hold on. Got it. Stop share. Hold on. Ooh, it's so dark. Yeah. There you go. Okay, so this is like a brand new thing after you open your Code Composer. So do new project. All right, so over here, the target section, right? There's TIVA-C or TIVA-E. We're using TIVA-C. And this is the reason we have TM4C like a G86PM, and that's it because I think I said in the beginning of the PowerPoint, it's because of the chip that's installed on the board itself. So because you're trying to talk to that chip, and then you want to select Stellaris, and that interface is what is used by the TIVA-C, actually TIVA-C in the Code Composer, to convert your compiled code, which is in assembly machine, to actually install on the microprocessor itself, right? So without this, you can't actually load your code. After that, you want to create an empty project with main.c because that's easier. If you're using RTOS, you'll have to download other libraries. We're not doing RTOS here. Your embedded processors class, embedded microsystems class with Dr. Lay, you'll be using RTOS. So you'll download that, and over there you'll have like an example, right? So we do this. Okay, oh yeah, I forgot the project name. I'll just call it. Yes.
So with this system, it is very sensitive. For some reason, for your path setups, have your directory, this project, in a C drive. Don't put it under your username with a space. Spaces in there will destroy the project. I've done that before.
Right.
I literally tried. Make sure it's in your C drive. Make sure there's no space.
Yeah. And I think it deleted mine too because I had something yesterday, and when I opened it, it opened a new one. So yeah, it's difficult to work with for no reason other than like I was debugging this and it didn't like the fact that I didn't have inc / in a relative file path, which is the whole point of a relative file path is that it's supposed to not care. But anyway, okay, and here now after you come to the project, so this was the test. Look, this is the one I was doing yesterday. And this is what I'm doing. Let me try to show you what I'm doing right here. So for some reason, this thing thinks that if I don't have this, it will not open this file, even though it's actually in the directory, which is dumb. You don't have to usually do that because in C and C++, if you use quotation marks to include files, you're saying, hey, I don't have a specific file path. Try to see it in the workspace. Usually it works with every other IDE, but for some reason, Code Composer is more picky. So the rest of the setting up here, you click on your project. Oh yeah, I don't know. My screen is kind of like that. Hold on. Yeah, let me see. No, that. Okay, I'll just do the PowerPoint. I think PowerPoint has the same thing. Yeah, sorry. It's just.
Control plus.
Oh, you can't see this one either?
No, on the CC.
Okay, Control plus. Yeah, no, my it's because my screen is slightly different. It's like it's the HD version. Wait, can I go restore? Yeah, wait, hold on a second. The appearance. I should be able to zoom in real quick. Did it zoom in? No, it didn't zoom in. Okay, sorry, but anyway, you got. If you can't see, you will see something called active/debug here on your left hand side. Yeah, just click on that and then right click, and then go all the way down where it says properties. Right, Alt plus Enter. Click on that, and it shows you a new window will pop up here, and you want to go to ARM compiler first. And in ARM compiler, you want to go to include options, right? And so in this file, since I haven't done anything, we're going to have to include the directory for our TIVA where we just download, because without it, it doesn't know that you're talking to us. So you click on this little file icon on your top right that has a plus, the green plus, you add, click on that. You click on browse, and then you'll open up a directory that is inside CCS. We just want to go to the TI one instead. And in here, we want to select this folder that's called TIVA-C_series. And the version will be different depending on what you download. Wait, am I going too fast? I'm sorry, because I am going way too fast, right? Okay. Okay.
Go back over.
Yeah. Oh, okay. Because I didn't ask nobody if I was going too fast. I was just breezing through. All right, select folder. And okay. I personally prefer to apply and close before I do the other stuff, just in case it thinks I didn't add it. So apply and close. We're done with part 1. Part 2, we do the same thing again, except instead of ARM linker, compiler, we go to ARM linker. And you open that, and here you want to go to you want to go to file search path, because we have to add a certain library that's inside of TIVA-ware. Why, I don't really know. I just know that we have to. So browse. You go back to that TIVA-ware folder like last time. Inside there, you'll see a folder called driver_lib. Open that. And then inside there, there's a folder CCS. You want to open that one. And then finally, you open the debug folder. And then you select the driver.lib file. You add it. And apply and close. And now you are good to go in terms of coding. See, now you can see these things are included here. It wasn't there before. And the code that I'm gonna give y'all today doesn't particularly use doesn't use any includes. But just to show you that it can open this, just to show that it does work, I'll copy that real quick. Oh. Yeah, let me do that. It will compile. It should compile. Hopefully it compiles. There you go, it compiled, right? And the reason why it can compile now is because if you had added this earlier, it wouldn't have known where to go look. So with all the things that we just added, it knows, okay, it knows the file path to look for this. This is the board we're using. Also, just to show that if I don't do that, it doesn't want to compile for some stupid reasons. And also, whenever you're trying to debug in Code Composer Studio, I will just say it's probably going to be the most difficult thing you've done in terms of debugging, because there's very little resources. And even the ones you'll find are from like 2017, 2011, and they're very old. Okay, so now for the code itself that we want to test with. Let's go here. Okay, there you go. That's the code. Can you share that?
I've already posted.
Oh, cool. Let's, can I do that?
Who doesn't have some more about it?
Yeah. And also in there, by the way, on the notes section, I also have added like the link to the page where it discusses what it actually does. In this example, it defines a lot of the things that is already defined under this file. Obviously, if you can include that and run that, it will not like it. For next workshop, we will be actually coding with this, so it's easier. I just wanted to just have like a ready-made code to debug with. Let me see if you can. Oh, did it download it from me? Downloads. No, it did not download it from me. Cool. Okay, that's fun. Let me stop sharing just for a second. Yeah, like it should be right here. Let me download that. Okay, let me go back to share screen here. Okay. Oh, so I'll open this. You guys have TIVA-Cs, right? You can connect it. Yeah, like to test this code. What it will do is essentially it's just a blinking code. It's gonna blink LED periodically, slowly. Right now, when you connect it, it's gonna blink actually like rainbow colors. What windows? Oh, here.
All the general functionality.
Oh yes, no, I did not do that. Okay, sorry. So here is. Let me just go slowly. So in here, this window is where you will do your coding, right? Your left-hand side is all of the projects you will have made. Again, because this is based on Eclipse, the open source software IDE, is very similar to that. So in the left-hand side, you'll have all your directories, and the ones that you're active will show you active/debug. And inside there, you'll have your files. The ones most of the time I've actually personally ever really used is the build thing to build, which is just compiles your code, make sure that it's compilable. And then the moment you have to, when it comes to loading, you have to connect to TIVA-C, right? And there's the little bug symbol. I think it's this one. It looks slightly different. You click on that. Hold on, I have to open my TIVA-C to show you that. Is there an open one? Can I borrow? Yeah, if not, I'll open this. Where is my key though? Wait, I don't have a key. Sorry, I seem to have misplaced my key, so I can't even open it. Yeah. Right. You need a key to open it? Thank you. Oh, it's open already? Cool, thanks. Thanks. I didn't even know I didn't have my keys. Oh, wait. Okay, let me. There's only. Oh, wait. Online can't hear me for a bit just because I only have one USB port. And yeah, and that conflicts with the USB-C port. So they will hear me from my computer mic, hopefully. Anyway, like I said, when you open for a brand new one, it's like this, right? This is also something you'll do in Dr. D's lab eventually. But in there, you'll be using the buttons to the side to control the amount of with pod module. Oh, I forgot to mention this. Sorry, I just realized. But the PWM module, you're actually seeing live right now your screen. The reason you get to control your brightness is with the PWM module. So whenever you increase or decrease your brightness, what you're really telling the computer is, hey, increase or decrease the frequency of the modulation. So the more brighter you want, the faster it's refreshing. Because all in your screen, all it is LEDs and LEDs. I think it is the capacitive or MOSFETs. I'm not too sure. I don't remember. But all you're really doing is again supplying voltage there, and the faster refresh just means keep supply faster, right? And then when you decrease it, you're decreasing the modulation frequency. It happens way too fast for us to see, but that's really what's happening. So that's why whenever you open your camera, you try to take a picture, you see like blue little lines, because that's like the frequencies interfering. And your camera really is just trying to capture light, which is just wavelengths, right? Okay, let's go to this. Okay, let me try to copy that code real quick here. Oh, wait, it's not even letting me call. Oh, it's restricted mode. Huh? Okay. Yes. Copy that. Again, like all of these defines that we see here, this is defined for you in that library, include TM4C123GH6PM. We just don't have that here because again, it's just not first, like it's defined here. So most of everything we need is defined here. Whenever you need extra things, let me actually go to the library for you. Okay. The reason all of this is X'd out is because it's a stupid Microsoft stuff. Let me go to TI real quick. Okay. You see your TI work. So you go to when you go to includes, you'll see all of these files. There was a reason why we download all of that. It's because whenever you're trying to use the modules and whatnot, you really are trying to include them. Because C by itself doesn't have that. So that's why Python and like even Java, the other JavaScript, they're easier to use and stuff because they have all these libraries built in. Whereas C, you don't have that. And that's also one of the reasons why C is preferred for microcontroller programming because it's the easiest to convert to assembly. It takes the least amount of space and also the fastest when you are talking to machines. Okay, cool. And this is, I don't know if I don't want to open that. Not right now. Okay, so now we worry about the code here. Let's see. Okay, let's see if it builds. I did I? Yeah, I did. Let's see if it builds. It builds. Cool. And now we want to debug. There you go. When you click this, it opens up this screen. And what it's really doing is it's executing it to your microcontroller. Right. So you can see how now there's no light in my TIVA-C anymore because the new code has entered. You have to reset. Which is because every time you upload new code, what happens with the TIVA-C is you're erasing existing memory and you're rewriting memory. And this memory is non-volatile. So that's the flash memory I was talking about. So you have to reset. It's the reset, but oh yeah. Also, make sure whenever you connect to the TIVA-C, please connect to the debug port because this is not, you don't use that. You want to use this when you program. This you can use for just simply trying to run the program, right? But this is the debug. Also, there you go. Now it's supposed to, this the whole code is that it blinks. Yeah, that is literally it for today. So if you can run it, you're good to go. If you can't run it, then we'll help. There we are.
So now I'm gonna turn on the lights and we'll help you guys out with setting up everything.
Yeah. Cool. Yeah, I think next. When is the next one we scheduled by the way for the workshop?
We'll talk about it.
Yeah. For that one, I think I will be using ADC converter. Do I turn this off?
You're gonna help them set everything up?
Well, let me know what.
You want the code?
I think so. Yeah, I mean, I will have to obviously ask. But nobody has asked. Oh yeah, okay, cool. So how fast did I go? Let me just ask in terms of the setting up, because I know I would just go.
Did anybody get Hibernation Studio put up?
Right?
I didn't get to that one.
You still sticking with you?
Oh, okay, cool. That does happen. It's gonna what it's gonna tell you is you're gonna have to restart. Eventually, when it's done.
It was the thing like this.
That happened.
You didn't install on the
Is it going cool? Okay. That's it, you run it? Yeah. That's okay. The problem with that,
I'm good.
Is the
Wait, is the switch turned on? There's a switch on.
Oh, yeah.
Things tend to work better around.
How far are you along?
Now.
Here.
You pick it up, you put it.
Yeah.
Yeah. You know what else? That's all. You have.
Yeah.
Oh, yeah. So.
This is my first workshop ever.
I mean, everything, I think it's just me. That's fine.
This
I miss out. I forgot, like, I think I got the
last time I took better class. I remember.
It's a lot of stuff. I think I get everything. It's just a matter of doing it also. I'm probably gonna be.
Yeah, yeah, taking that out.
Yeah, explaining why. How.
So which one are you from?
Oh, yeah, there's one.
Go to you now.
It's Liberty.
Oh, you go to the, you want to get.
Yeah.
You may not. It's managed to get some like. You may want to. Wait, hold up. Yeah, I messed it up. Well, you're downloading. I mean, you're not. I forgot to study a lot. Like I didn't.
To be fair, like, that was the last. I don't think. Yeah, I know. It's so weird how like so like you like have like.
Yeah, I didn't expect whatever.
Wait, so like. I got half. So I'm.
They're just better to use.
I got. I didn't do it. Oh, it's a split.
Yeah.
So 10 for part A, 10.
Oh, that gives you the entire one. You want all of it, or you just want the book? Yeah.
You got it.
I'm sleepy right now.
Yeah, take it as the. I know we're popular.
How far are you guys in?
I can sleep once I get caught up in electronics.
Yeah, see, that's-
Oh, electronics.
I think what you can't even do.
Yeah.
Down